asked you to investigate this matrix before the program, and in particular to calculate its eigenvalues and its eigenlines. What you found was that the matrix has eigenlines x minus 3y equals 0 and 2x minus y equals 0, and these are the corresponding eigenvalues. What does this mean? It means that for a point on this eigenline, for example, x minus 3y equals 0, when you apply the transformation represented by the matrix, the point is scaled by a factor 2. And similarly, a point on the other eigenline will get scaled by a factor 2/3. So we know a certain amount about this matrix, or rather about the transformation that it represents. But so far we only know how it transforms points on the two eigenlines. One of the things we're going to investigate in this program is what happens to points which are not on the eigenlines. Then we'll be able to use the geometry of the situation to help calculate powers of this matrix. As you know, calculating even the square or the cube of this matrix involves you in some pretty heavy arithmetic. If we'd asked you to calculate before the program, say, its 10th power, that would have seemed an act of extreme cruelty. But by using the geometrical insights that we'll gain in this program, we'll be able to write this matrix in terms of some rather simpler ones. And as a result, the calculation of powers will become quite an easy process. Now, earlier in the unit, you looked at a somewhat similar situation for this other matrix. Again, there are two eigenlines, but this time they're at right angles to each other. And that's the crucial difference between our two matrices. It makes this second situation rather easier to deal with, because as you saw, you can use the fact that the eigenlines are perpendicular by rotating them so that they line up with the coordinate axes. And this helps you to see how points not on the eigenlines transform. Now what we're going to do is to show you how the approach that we used in this case can be modified to cover the more general kind of matrix that we started off with. But first of all, let's remind you in detail of what you found out about this matrix.
Well, in section 1 of the unit, you saw that this matrix can be expressed as the product of three matrices. There's a rotation through the angle pi over 4, and I've called that matrix R. Next, there's a matrix which has terms on the diagonal, which are the eigenvalues of the original matrix. That's 2.5, and the terms off the diagonal are both zeros. And lastly, there's a rotation matrix through an angle of minus pi over 4. Now, this first matrix R was a rotation through pi over 4, so this matrix is its inverse, R to the minus 1. Now, matrices like this center one, that's to say matrices with 0 off the diagonal, they're going to play a crucial role in what we're going to do. And we call matrices like that diagonal matrices. Well, let's just look at what this product of matrices means from the geometrical point of view. This diagram represents the transformation corresponding to the original matrix. These are the eigenlines, and we scale along this line with a factor of 2, and this one with a factor of 0.5. Now let's see what this expression means geometrically. Now, when you apply the product of matrices to a point, you apply the one on the right first of all. And this one is a rotation clockwise through pi over 4. It takes the eigenlines round to the axes. Next, there's this diagonal matrix which scales along the x-axis with a factor of 2. And along the y-axis with a factor 1/2. And lastly, there's a rotation back through pi over 4, which takes the axes back to the eigenlines. Well, you've already multiplied out the right-hand side, so you know that this product is the same as the matrix on the left. What I want to do now is to illustrate geometrically that they represent the same transformation. That means that if I take a point and I transform it by this, it has exactly the same result as if I take the same point and transform it by this, followed by this, followed by this. For example, let's take a point on this eigenline. What happens to it? Well, r to the minus 1 rotates it down to the x-axis. And then the diagonal matrix scales it by a factor of 2. And lastly, r rotates it back to the eigenline. So the overall effect is to scale it along the eigenline by a factor of 2, which is exactly what the original transformation did. And similarly, a point which is on the other eigenline gets rotated to the y-axis, and then it gets scaled with a factor of 1/2, and then it gets rotated back again. So the product does the right thing on that eigenline as well. Right, we've seen what happens to a point along the eigenlines. But the trouble is it hasn't guaranteed what happens to points which are off the eigenlines. So let's look at that problem geometrically and see what happens to those points. But the way we're going to start is by seeing what happens to a line parallel to one of the eigenlines. Its image is a parallel line. How far has it moved? Well, this point on the other eigenline is moved out by a factor of 2, so the whole line is moved out by a factor 2. Now let's look at a line parallel to the other eigenline. Well, we know what happens to this point. It's scaled by a factor of 1/2. So the image line goes through here. So that's what happens to lines parallel to the eigenlines. But what we're really interested in is what happens to a point like this. Well, in order to find out, we'll put a line through the point parallel to one of the eigenlines. We know what its image is. Then we take a line through the point parallel to the other eigenline. Here's its image. So the image of the original point must be the point of intersection of the two image lines. Now we can see what happens to any point in the plane if we draw up a grid of lines parallel to the eigenlines. And we'll look specifically at what happens to this point. It's at the intersection of these two lines which transform to these. So the image point is this one. It's easy to see what happens to the other points as well. Now here we've been looking at what happens when we apply the original transformation matrix directly. Let's now see what happens when we apply the equivalent 3 transformations. First of all, we rotate the points clockwise through pi/4, taking the grid with us. The next transformation doubles the x-coordinates and halves the y-coordinates. And lastly, the third transformation rotates the axes back to the eigenlines. And that demonstrates why the overall effect of the 3 transformations is the same as the original on all points of the plane. So that's the geometric argument which shows that if you do the 3 transformations corresponding to these 3 matrices, you get exactly the same result as you do when you apply this matrix. You should also notice that because of the parallel lines argument, once you know how the transformation affects the points on the eigenlines, then you know what it does everywhere. What we're going to do next is turn to the question of finding powers of this matrix. You've done the calculation which shows that this raised to the power n is r times this diagonal matrix raised to the power n times r to the minus 1. But what's the geometry that's going on? First, let's look at the square of the matrix. That means applying the original transformation twice. We apply it once, and we apply it again. Notice what has happened to the points on the eigenlines. One's been scaled by a factor of 4, that's 2 squared, and the other by a factor of 1/4, that's 1/2 squared. To get the cube of the transformation, we have to apply the original transformation one more time. Now the points on the eigenlines have been scaled by factors 2 to the power 3 and 1/2 to the power 3. So that's what happens when we carry out the transformations for the square and the cube of the matrix. The eigenlines remain the same, but the eigenvalues change. For the square of the matrix, the eigenvalues are the squares of the original eigenvalues. For the cube of the matrix, we get the cubes of the eigenvalues, and each time we apply the transformation, the eigenlines remain the same, but we get an extra factor in each eigenvalue. So for the nth power, we still have these eigenlines, but the eigenvalue here will be 2 to the power n, and here it will be 1/2 to the power n. And that means that you can write the nth power of this matrix like this. It's exactly as the same form as the original. There's a matrix here and its inverse. And there's a diagonal matrix in the middle. Well, why does it look like this? Well, the r and r to the minus 1 are the same matrices as before because we have the same eigenlines. And the terms in the diagonal matrix are just the eigenvalues for the nth power. So geometrically, that means take the eigenlines to the axes, scale along the axes, and then rotate back.
So we've seen in great detail the geometry of the matrix with perpendicular eigenlines. But let us now go back to the problem of dealing with the matrix we started the program with. So far, all we know about it are its eigenlines and the corresponding eigenvalues. We know, therefore, that points on the eigenlines get transformed by the appropriate scaling factors. But this time, the eigenlines aren't perpendicular. In the simpler situation we've just been considering, we found out a whole lot more about the transformation. Can we repeat that procedure for this more complicated matrix we're looking at now? There were 3 things that we found out about the simpler matrix. We found out what happened to points which are not on the eigenlines. We were able to write the matrix as an expression involving a diagonal matrix. And by using this, we were able to calculate the powers of the matrix. So what we're going to do next is to look at what happens to points not on the eigenlines for this matrix. Having dealt with that, we're going to show that even though the eigenlines aren't perpendicular, we can relate this transformation to a simple one which involves scaling along the coordinate axes. And then we'll use that result to help us to calculate the powers of the matrix. But first we'll look at the question of transforming points off the eigenlines. We want to find out what happens to a general point in the plane. What we did before was to see how lines parallel to the eigenlines are transformed. If these lines transform into parallel lines, as in the previous situation, then we'll be able to predict the transformation of any point. But do they transform into parallel lines?
So let's find out what happens to lines parallel to eigenlines. Let's look at this line, which is parallel to the first eigenline. We'd like to prove that it transforms into a parallel line. But you already know from the parallel line property which you proved before the program that given any 2 parallel lines, they transform into another pair of parallel lines. So how does this apply to our particular situation? Well, here's a pair of parallel lines, so we certainly know that they transform into another pair of parallel lines. But this one happens to be an eigenline, so it transforms into itself, which means that this one transforms into another parallel line. So lines parallel to the first eigenline transform into parallel lines, and the same is true for lines parallel to the second eigenline. So how does this tell us how points transform? For this point, all we have to do is to draw the grid of lines through the point parallel to the eigenlines. We know that the images of these are again parallel to the eigenlines. But which parallel lines? Well, we know the images of these points. They're scaled by their eigenvalues. So these are the image lines, and this is the image point. Okay, let's see how the transformation works for some other points. This grid transforms into this one.
So by using much the same constructions we used in the first part of the program, we've been able to find out how points not on the eigenlines transform. The next thing we said we would do is relate this transformation to one which scales along the axes. By doing this, we'll be able to see how to express this matrix in this form. Some matrix Q, followed by a diagonal matrix, and then the inverse of the first matrix. As before, this diagonal matrix will have the eigenvalues as the diagonal elements. Remember, that's the matrix which gives the scalings along the axes. All we have to do is to decide what we have to take for Q. Well, here we can use the clue that was given by our earlier investigation. The key thing there was that we had a matrix which transformed the x-axis to one eigenline and the y-axis to the other. So what we've got to do now is actually find a matrix Q which does the same in this case.
So we want to write our matrix as Q, D, Q to the minus 1, where D is this diagonal matrix, and what we need to do is find Q. But what does Q do? It takes the x-axis to this eigenline, and it takes the y-axis to this eigenline. And I'm going to do that, first of all, by taking this point, 1, 0, which is on the x-axis, and transforming it to the point above it on the eigenline. And that is the point 1, 1/3. Well, in fact, the image of 1, 0 just gives me the first column of my matrix. So the first column of Q is 1, 1/3. Now I would take the point 0, 1 on the y-axis and transform it across to this point on the second eigenline, which has coordinates 1/2, 1. And the image of 0, 1 gives me the second column of my matrix, and so the second column of Q is 1/2, 1. All right, let's just check that any point on the x-axis does get transformed to the first eigenline. So let's look at the point with coordinates x, 0. And let's see what happens when we apply the matrix Q to that, to x, 0. It's 1 times x plus 1/2 times 0, which gives us x, and then 1/3 times x, 1 times 0, gives me x over 3. So we have this point up here, x over 3, which sure enough is on that eigenline. But in fact, we knew that anyway, because the origin gets transformed to itself. This point gets transformed to that, and since lines go to lines, the line connecting these 2 points is transformed into the line connecting those 2 points. But we can get some more information out of that too, because it will tell us precisely how QD, Q to the minus 1 acts for any point on the eigenline. Well, first of all, this point gets mapped down here by Q to the minus 1. When we apply the transformation D, all D does is scale along the x-axis by a factor of 2. So we get the point 2x 0. Now lastly, we have to transform 2x 0 by Q. Here's Q, multiply it by 2x 0. 1 times 2x, a half times 0, gives us 2x. A third times 2x, 1 times 0, gives us 2x over 3. So this point gets transformed up to here, which has coordinates 2x, 2x over 3. So we can see that applying the 3 transformations does scale along this eigenline by a factor of 2 because the coordinates have just got multiplied by 2. And the same thing happens along the other eigenline. If we take a point on the other eigenline, it will be scaled by a factor of 2/3. So now we know that q dq to the minus 1 does the same thing as the original matrix for all points on the eigenlines. And by the parallel lines argument, the same thing is true for all points in the plane. The original matrix and q dq to the minus 1 give the same transformation.
So now we've found a matrix Q such that our original matrix can be written as Q times the diagonal matrix times Q inverse. Can we use this expression to help us simplify calculations of powers of our matrix? That was the third question we raised. And once again, the geometry of the situation will help us understand the problem. Well, let's run through exactly the same strategy that we adopted before. Again, we'll start by looking at the square of the matrix. We carry out the transformation once, and then a second time. The eigenlines are the same. The eigenvalues get squared. Now, let's look at the cube. The eigenlines are still the same, and the eigenvalues get cubed. Once again, a similar kind of thing is going to happen for any power of the matrix. We'll have the same eigenlines, but the eigenvalues of the nth power of the matrix will be the nth powers of the eigenvalues of the original matrix. So now we can see how to write the nth power of this matrix. It's q times this diagonal matrix times q to the minus 1. The same q because it's the same eigenlines, but the entries in the diagonal matrix are the new eigenvalues, 2 to the nth and 2/3 to the nth. And to calculate this product of matrices is much simpler than to calculate, say, the 10th power of the original matrix directly. This program has been concerned with how you express a given matrix in terms of a diagonal matrix and with an application of this result. This process of writing a matrix in terms of a diagonal one is important. So to end the program, I'll just run quickly through the steps involved. First, you find the eigenvalues of your given matrix. They give you the entries of the diagonal matrix. Then you need a matrix Q, which takes the x-axis to one eigenline and the y-axis to the other. When you know the equations of the eigenlines, it's easy to write down such a matrix, as Bob showed earlier. Finally, you can calculate q to the power minus 1 simply by inverting the q you have found. And that's all there is to it.